over previous efforts. I believe this might have been my third one or something here. I'm not really sure on them anymore. I think I must have built 6 or 8 of these things, different variations on it. This one's a little higher quality, flat surface. Got a little better at capping the ends and brazing everything together. Again, this one uses some kind of a copper screen. I think I got it at an art supply store. However, it wasn't really fine enough, I think I found out later. And keeping that really close to the surface is very important as well. So another one here, I'm not quite, this one was never cut open. A little bit higher quality. I got a little bit thinner because eventually my intentions were to, instead of putting the thermoelectric device on the bottom, was to put this thing vertically, and then I could actually put Peltiers on both sides, you know, perhaps 4 to 6, 3 on each side, and then the liquid would wick up through a material on the inside here and then vaporize and then pass out towards the top, you know, perhaps at the end. So that was an improvement. Each one of these came with improvements in performance. I got from like 45C down to 22C, down to 12C, down to like 9C. I think this was at about 200 watts over about 150 square, 1,500 square millimeters. This here was one of the last ones that I built, and this one has material on all sides, and it has a very fine wicking material, very fine screen. There you can see it's a very, very fine screen, and then inside kind of has a very coarse screen, and that's mostly just to keep pressure on the fine screen, keep it up against. And then there's this. This is actually a piece of wool. It's copper wool. I call it a copper tampon. So I kind of rolled it and stuffed it in there to keep pressure against the flat areas, and potentially also to distribute the wicking of the liquid across the surface. So there's a lot of different interests that I had here on the way this worked, and part of me wishes I would have continued the project, because just the design of the evaporator itself was very fascinating. This is that copper wool material. It actually came from locally here in Oregon. I'm not sure where it's manufactured. So it's a little expensive there, but what I needed to fool around with. Now, mostly I worked with about a 3/8 inch riser to the condenser. Now, I just want to give you an idea of the scale that I was working with. Now, this is a work platform. There's another video on a dryer, a refrigerated dryer, which is this assembly here in the back, and there's a compressor back there. It's unimportant, but this assembly work platform here did have the evaporator mounted here at the bottom with a aluminum plate, a series of cartridge heaters that was clamped to it. There's a clamp mechanism here, and plastic cross piece, and then up here is where the condenser was mounted with a fan on it, and then a series of controls and switches, power supply, and for monitoring the wattage, things of that nature. And then I had a series of thermocouples mounted all around it, and that I might as well show you. These are some of the condensers that I was using. These are brass and copper air conditioning condensers, or excuse me, heater cores, water coolant heater cores out of automobiles. I'll get into those here in a minute. And then this was a shroud, a fan shroud, which was mounted on there, and this whole assembly was fixed up there. So in some of the other videos, you can see it actually probably put together what it kind of looked like. So the condenser itself, right here is the first condenser that I used. Now, choosing the condenser was actually really important, because a normal condenser that you would see in a refrigerator or any kind of air conditioner, any kind of HVAC application, is usually going to be it's copper and aluminum, copper tubing, serpentine back and forth through aluminum tubes, and it circulates back and forth. Usually it's a pretty small diameter. Might be a single run of tubing, might be a multiple runs of tubing if it's a large condenser. these are designed for active systems, where you have a large pressure differential from one side to the other that allows for the circulation to occur. I'm dealing with a passive system, so I'm only dealing with very small pressure differentials in terms of vapor pressure across the system, and that is important because a serpentine system like that, although it might be made to work with sufficient airflow across it, it's going to be very difficult to get to prevent liquid slugging inside that would block the condenser tubing. It'd be very critical that the entire device be, perfectly level. Too many issues with that. So what I want is a lot of surface area in the condenser, but not a but almost vertical, if not perfectly vertical, downcomers through the condenser, which is what an old style brass and copper heater core allows you to do. This thing's filthy. Now, in a heater core, this thing is designed for liquid, for water and coolant, and in the majority of them, even the modern aluminum ones, you actually have an inlet and an outlet. So in the inlet, liquid goes in there, and then there are tiny micro channels that go all the way down to the bottom, and the bottom plate is open, and then it travels across, and then back up the other side, and out the other one right there. So actually that wasn't going to work for me, so I had to connect those two together to make those the evaporator, from the evaporator for the condenser inlet, and then drill a hole in the bottom and put a piece of 1/4-inch tubing there to serve as the liquid return or the downcomer back to the evaporator. This thing was a real bear because this cap is soldered on, so I had to do a lot of soldering on top to prevent overheating and damaging this thing. And I ended up getting a lot of flux in there in the process of doing that soldering, and made a big mess and contaminated my evaporators and had funky numbers and all kinds of problems. And hindsight's 20/20, but it was stupid. So eventually I moved on to another evaporator. This one is a slightly different construction in terms of the way that it's assembled, but same principle, whereby you have these essentially microfins. These are very micro channels, very small channels there. These things could be found in automobiles, probably going back to the 50s and on up until maybe the early 90s or something like that. They're relatively inexpensive. I don't remember what I paid for it, but if you look around for them, you can't find them. Now you'll notice that this one has an inlet in the top and inlet in the bottom. Perfect for my application. It is about a 5/8 inch pipe on the top and bottom. I think they are brass or copper with brass on them. I'm not sure, but it was much easier for me to modify this for my application. I was much more careful about getting flux inside, and I tried to thoroughly clean these things after I used them, or after I assembled them, to get any flux out so it didn't contaminate the rest of the system. I did start to add thermocouples to the head of the condenser in order to measure the vapor temperature on the inlet, as well as the vapor temperature of the outlet of the evaporator, to look for any slight differences there. And in the process of doing that, I foolishly busted a hole straight through the microfins, or the micro channels on the other side, and then dropped it full of solder, eventually sealed it, and still contaminated the thing, and just stupid. So eventually I think I moved on to this third one here. It's the same construction as the last. It's a slightly taller, 1.5 inch taller or so, and I was able to successfully put a thermocouple in the top, and I took a lot of good measurements all around the system. Here you can see where from the evaporator traveled up into the top of the condenser, bent a piece of pipe to do that. I didn't have any 5/8 inch tubing, and then I had to adapt the large. Anyway, not too important. So, what did I find? Let's pause for just a second here. Alright, so what did I find? First, I'd like to apologize to anybody that's interested in this subject, that I'm a very poor orator. There's a lot of information to try to get into a short video, and I stopped this work in roughly August, so it's been several months now. It was a little refreshing. I can get back into it pretty quickly, but it's a lot. It's a lot of stuff, and I did a lot of research and read a lot of patents and a lot of papers on the subject, having to do with nucleation, studying nucleation, different types of materials, and the way that vapor travels, trying to get that unidirectional flow. One of the things that I found was lacking was condenser design. And from very early on in my research, trying to look at different university studies and theses and things like that, I found a shortage in types of condensers that are being utilized. I've even saw quite a few serpentine, copper, and aluminum condensers built for refrigeration systems being used for this application. And I just don't think it's really ideal. This thing is a heat transformer, and we're trying to go from, like I said, a high heat flux in the evaporator to a lower heat flux, much more spread out in the condenser. And the problem that I see with these microfin condensers, microchannel condensers, I keep fouling that up, is that what I think was happening as I was getting a lot of for lack of a better word, capillary action, the wetting of the refrigerant, of the alcohol in the channels of the condenser, it was sticking and it wasn't falling by gravity very effectively. So if you had something that had a little bit larger microchannel, that those droplets were able to fall more effectively, I think would have worked a little bit better. And in all the testing that I did under infrared, and you can look at some of the videos and kind of see what I'm talking about, I was only utilizing maybe the top third of the condenser that was actually probably doing real condensation, and the rest of it would have been some degree of subcooling, if you will, whereby some of that liquid was held up. The reason I think it was held up is because at certain times you would see the warm area of the condenser shrink slightly, and then suddenly it might grow, and in many cases that would be preceded by one or two of the channels getting very warm, and you could literally see where the liquid was dropping and then there was vapor being condensed there, and there was a lot more heat being released. So maybe it's not an ideal choice as a condenser, but frankly, I haven't seen a design out there that is ideal for this small application. Now, excuse me. So one of the things I've tried to do, and this isn't going to make a lot of sense because it requires probably a whole nother video to try to explain it, was, let me say this. Between the evaporator and the condenser, you have a vapor line, and based on the amount of heat that's being pumped into the evaporator, and once this system has come to something of an equilibrium, so you're putting 200 watts in, the temperature rises by, let's say, 15 Celsius over ambient temperatures. So it's 25 Celsius in here. This thing rises to 40 degrees Celsius. The plate, the heater. That, to me, that means that as long as you're controlling the amount of leakage around, we thoroughly insulated around the heater and around the evaporator. So essentially, all of the heat that's being put into the evaporator is coming out of the condenser. So we have that 200 watts. It's heated up by 15 degrees. We more or less know what the latent heat capacity of the alcohol is. The sensible heat, as far as any temperature changes in the alcohol, is pretty negligible, I think, for this application. So we focus on the latent heat. We should be able to calculate roughly what the mass flow of the alcohol is through there. And if purely vapor is rising out of the evaporator and going into the head of the condenser, then based on the diameter of that tube and some assumptions about the type of vapor flow through there, the type of gas flow, turbulent or laminar flow, whatever, we should be able to estimate what the velocity is through that tube. So we get that number and we say, it's 50 meters per second or something like that. I don't remember what the actual number is. It seemed high to me at the time, and I don't have the math skills or the experience to say what's high in this case, but any velocity at all is going to encompass some kind of losses. We have taken heat, we've evaporated alcohol, we've produced vapor. that vapor increases the pressure, the vapor pressure. The vapor pressure in the condenser is risen. The cool ambient air cools that metal, pulls some of those